All right, let's do an example with projectile motion. So here we have a projectile that is fired horizontally at 95 meters per second from a height of 35 meters. How far away will the projectile land? So with the projectile motion question, the first thing to do, that's always a good idea, is to draw a sketch. So we're going to have some kind of height, some kind of distance, and let's label some values that we know. So we know that the initial velocity of our projectile is 95 meters per second horizontal. So let's label this. Let's label this 95 meters per second, and I've drawn it horizontally, so there's no angle. It's flat with the horizontal. We'll see some other examples later on with angles, so if you're interested in seeing those examples, you'll be able to find more on my channel. But in this case, we have a horizontally fired projectile. All right, let's also look at the height. We're given 35 meters, so I'm going to do this in a different color. We know that the height, which is, here, let me just label this as a height for now. This will be 35 meters. So we know the height is 35 meters. All right, and there's another value that is unknown, but I'm going to write it down here. That is, so our projectile is going to follow some kind of motion like this, right? It's going to hit the ground. It's going to start off going horizontally, and with gravity, it's going to start slowly coming down to the ground, and at some point, it'll hit the ground. And that point, which is delta dx, we don't know. We don't know what value that is. All right. So again, with any question like this, I encourage you to draw your little sketch like this to give all the information that you know and some of the information that you don't know, and just get it all labeled and organized. So we're asked to find how far away will the projectile land. So the formula for that, the formula for, I guess that's a variable, delta dx. Delta dx, well, that is equal to the velocity in the x direction multiplied by time. So again, our variable delta dx, so the distance traveled in the x direction, let me label these. This is our x, and this is our y. Those are our axes. So the distance traveled in the x direction depends only on the speed in the x direction, so in meters per second, multiplied by the time that it travels in seconds. And we know this value, right? The velocity in the x direction, because our object is fired horizontally. This is the velocity in the x direction. So we know that, but what is t? T, we don't know. I'm going to write this, that we do know Vx. Vx is equal to 95 meters per second, right? Now the next question is, how do we find t? So how do we find t? t asks us, well, how long is it before this object hits the ground? So how long does this take? So how do we find t? It's how long the projectile takes to hit the ground. Takes to hit the ground. So how are we going to do that? Well, we have some tricks that we know from our linear kinematics. So this is our one-dimensional kinematics. So linear kinematics in the y direction. So we're going to do our linear kinematics. Put an exclamation mark on that. So our linear kinematics, but only along the y-axis. So I'm gonna continue with this, and I'll try to explain this as clearly as possible, and hopefully everyone's able to follow along. So with our linear kinematics problems, you'll remember that step one is to organize our variables. Step one, organize variables. And it's important to keep in mind that this is just in the y direction, right? So the first variable that I want to know is our v1y. So what is our initial velocity of the object in the y direction? Well, when it's fired, we got 95 meters per second horizontally, but is there any velocity in the y direction? Well, right when it's fired, no. So the velocity, the initial velocity is 0 meters per second. 0 meters per second. So what we're going to be doing is looking at this object. We're going to be looking at this object. I'm going to try and draw kind of a ball to represent this projectile. So this object flies like this, right? But when we're looking at it only in the y direction, we only care about what it does along this axis. So when it's fired, it has no y velocity, and then as it travels, the acceleration of gravity brings it down closer to the Earth, faster and faster. So it's going to start off dropping slowly and then faster and faster come to the ground until it hits the ground. And that point is over here, right? All right, let me continue on with our variables. So our acceleration, as we know, on Earth, is negative 9.81 meters per second squared. So that's the acceleration that this object is going to experience. Wow, sorry about that. This object is going to experience as it falls down to the ground. And then another variable that we know is the change in position. So remember, this is just in the y direction, so delta dy. Well, that's this value. So the change from the time we start measuring to the time it hits the ground is going to be traveling this distance. So negative 35 meters because it's down, right? This is from where the object is released to the ground is down 35 meters. And then the variable that we don't know that we're trying to find is time. All right, continuing on. Step 2 is to choose an equation. Choose equation. And then what we're going to do is we're going to look at our variables. v1, acceleration, delta d, and time. We're going to come over to our chart here, see which one of our equations uses all four of those variables. So v1, delta d, acceleration, and time. So this is going to be equation 2, the one that we're going to use. So because we have v1, acceleration, delta t, and time, that tells us to use equation number 2. And this step should be straightforward from now after we've done so many examples with this. Move to step 3. Going to plug in our variables. Plug in our variables. So let me first rewrite equation 2. So from the table, remember it was delta d is equal to v1t plus 1/2 acceleration times time squared. And let's plug in these variables. I'm going to keep them in green so we can keep track of them all. So our delta d, negative 35 meters, negative 35 meters is equal to our v1, remember, 0 meters per second. So I'm going to write 0 meters per second. And time was our unknown, so I'm going to leave it as t, plus 1/2 times our acceleration, which was negative 9.81 meters per second squared. So negative 9.81 meters per second squared. And then our time, again, our time is unknown, so I'm just going to leave it as a t. Leave it as a t. And then it was squared. And before we move on, I'm just going to clean up this equation a little bit. So 35 meters is equal to the 0. This cancels out. So this whole term goes to nothing. And the 1/2 times the negative 9.81 will have negative 4.905 meters per second squared multiplied by t. I'm going to keep that green, squared. All right. And now our next step is going to be to use the quadratic formula because we have a t squared. So that means we're going to have to use the quadratic formula to solve for t. So I'm going to write that. We're going to go back up to the top of the page. Go to step 4. Step 4, quadratic formula. So if we remember the quadratic formula, it's that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And that is when we have our equation in the form of ax squared plus bx plus c all equal to 0. So let's take this equation down here and bring it back up here. So I am just going to copy this and bring it up here to paste. And we need this equation in standard form so that we can use the quadratic formula. So I'm going to rearrange this equation. This t squared I'm going to bring to the other side. So I'm going to write this out. When we bring it to the other side, it becomes a positive instead of a negative. I'm going to get rid of the units just for now because they're just going to get in our way when we're using the quadratic formula. And I'm going to add this term back. That is 0t. You'll see why in a second. And minus 35, all equal to 0. So this equation is the same as this equation, but rewritten in the form ax squared plus bx plus c is equal to 0. I'm going to label these. This is our a value, this is our b value, this is our c value. So I hope you can follow along with this, and hopefully the quadratic formula is something that you've seen before and are familiar with using. So I'm going to just move along and start plugging in the values to the quadratic formula here. So t, here's our quadratic formula, is equal to, and I'm just going to start plugging in these values. So negative b, well, b is 0, so 0. I'm going to write that 0 anyway. 0 plus or minus the square root. And again, our value for b is 0, so 0 squared times minus 4 times a times c. So c is our 35. And remember the negative 35. All over 2a, so 2 times 4.905. Alright, so and that gives us that t is equal to plus or minus the square root of 686.7 divided by 9.81. And I encourage you to try this along with me. Type this into your calculator and see if you get the same answers. So as we know with the quadratic formula, we get two different answers. Here we have that t is equal to, when we do plus the square root here, we're going to get an answer of 2.67 seconds. And if we do minus the square root, we'll get a value of negative 2.67 seconds. And so which value are we going to use here? Only one of them is a real possibility. Only one of them is a real time. And we know that time cannot actually be negative. So this one here, we can't use. It's just an imaginary solution. So we can't have a negative time, obviously. So the solution we're going to use is this positive one. This positive one here, that will be our time. So that tells us it takes 2.76 seconds for the projectile to hit the ground. So again, we just found that from the time that this projectile is fired to the time it hits the ground, or to the time it hits the ground, if we're just looking at it the y direction, it's going to be 2.67 seconds. Right? Just want to move this up a little bit. And then that brings us to our final step. So step number 5 is going to be to plug our value for t. So plug in t. So remember this equation that we started with at the beginning? And we didn't know what the value for t was? Well, now we know. Now we have a value for t that we just found. So we're going to go back to that formula where delta dx is equal to t times the velocity in the x direction. And now we have values that we can plug in. So time, remember, is 2.67 seconds. That's what we found in the last step with the quadratic formula, 2.67 seconds. And our velocity in the x direction, remember that was the value we knew right from the start, 95 meters per second. That was the velocity in the x direction, 95 meters per second. And remember, this 95 meters per second, that horizontal velocity is maintained throughout the entire time that the projectile is in the air. We're not taking into account air resistance that would slow this down, so the object maintains the same velocity in the x direction throughout its entire time in the air. So let's multiply these two together. Delta dx is equal to 253.65 meters. So when our final answer, I'm going to round this off to 254 meters. And I want to write a little statement along with that. So the object, therefore the object lands. It lands in answer to our question, how far away will the projectile land? Therefore, the object lands 254 meters away. And that is our final answer.